Good afternoon, everybody. It's a great pleasure to have Felipe Almeida with us today. Felipe was a student at Valongo and then did a direct doctor PhD program in Valongo also. Then he came here for a postdoc of maybe five years.
5 years.
And he spent one of these years in a Noir lab in Tucson. And I have to say that Felipe was one of the main people behind S-PLUS and the success of S-PLUS. He was specifically the person behind the calibration of the data, which was really hard to do, and he got this done in a very good way. And we're very happy that now he has a position in INPE waiting for him. He has a jovem pesquisador in INPE, and soon will be a staff member at INPE. So it's
hopefully
it's a really a great pleasure to have you back here, Felipe. Go ahead.
Thank you very much, Claudia. It's my pleasure to be here. I think it's the first time I'm going to give a seminar here at IAG. And I think it's a good time because I'll be talking about mostly the results that I got during my postdoc here at IAG. So Claudia mentioned I worked in the calibration of S-PLUS. This was the main use of my time during the postdoc here, but I also worked with science, and today I'm going to focus on the scientific results. Just to give a brief overview before I start the presentation, I will give a quick introduction about galactic archaeology, because this project can be thought of as one of the projects related to galactic archaeology, so I think it's good to give a brief background on that. I will mention the S-PLUS survey. I know a lot of people are tired of hearing about S-PLUS, but I also think it's important to always explain, because if there's someone new in the watching the presentation, I think it's good to present S-PLUS to everyone. And it's the main data set that we're using in this project, so I think it's important to mention. And then I'm going to talk about the low metallicity stars that are the main target of this project. We're looking for these ultra metal poor stars. I will explain what this means. And if I have time, I'm going to talk about a little bit about galactic structure and other projects that I've been developing. So starting the introduction, this is what ChatGPT thinks galactic archaeology is, which is not that far from reality, because each project is indeed one piece of the puzzle that we're trying to build to understand the main questions that we ask in galactic archaeology. There are others, but these are the ones I think are the main questions. How is our galaxy currently structured? How did it form, and how did it evolve? It's not an easy task to understand this, because we are inside the galaxy observing only one time frame of the structure of the galaxy. But we call this galactic archaeology because we have the stars that we can use as fossil records of the history of the Milky Way. So I'm not going to read this because of the time, but this is basically what I explained what is galactic archaeology. The use of stars as fossil records, because there are three main properties that we can use. The first one is the one related to the position and motion of the stars, because the stars, they retain a memory of their origin. If the star was formed in the disk, the thick disk, the halo, if it's a star that was accreted by the Milky Way, the motion of the star, it evolves with time, but there is some memory that the star retains through time. Also, the chemical abundances are very important, because it's a record of the abundances of the interstellar medium of the time the star was formed in the Milky Way, of the region that the star formed. And also a very important parameter, which is the most hard one to get, are the stellar ages. It's very hard to get precise stellar ages, but they're very important because they tell us which epoch of the galaxy these other properties are related to. So it's very important to obtain stellar ages as well. Just to give a quick overview about the structure of the galaxy, this is very hard to point. This is the classical view of our galaxy. We have, I'm not going to use the pointer. We have a thin disk, which is basically rotationally supported. It's where most of the stars are, where the gas of the galaxy is, and it's currently forming stars. There is a thick disk that formed earlier than the thin disk, and in a much quicker time frame. the halo of the galaxy, with now we know an in situ population and also an accreted population, globular clusters around the halo, the sun is in the disk of the galaxy. So this is the classic view of our galaxy. We know this for a few decades now, like 50 years or more. This is already currently understood. But now we are seeing that the real situation of galaxy formation, structure, and evolution is much more complex than this. We have, for example, a corrugated structure in the disk of the galaxy, showing that the disk is not necessarily dynamically stable yet. We have many stellar streams that are remnants of mergers in the history of the Milky Way, or also globular clusters that are being dissociated by the gravity potential of the Milky Way. And we have, for example, the Sagittarius stream, which is the major ongoing merger of the Milky Way that we're currently observing right now, and can possibly be related to the non-stability that we observe in the disk, for example. This is just to give an overview that there is a lot of open topics still in galactic structure, and one of the goals of galactic archaeology is to understand this formation and structure of the galaxy. This is all in the context of chemical evolution as well, because the stars are being formed in this interstellar medium, but they are also enriching this interstellar medium. Different stars are producing different elements at different stages of their evolution. So for example, a sun-like star right now is burning hydrogen, forming helium. At a later stage, it's going to form carbon and oxygen. During the asymptotic giant branch phase, it's going to form the S-process elements. While the massive stars, they undergo a totally different evolution. They form elements up until the iron peak elements during their evolution, and then in the supernova phase, they can form, for example, the R-process elements. This is a very complex scenario, so we have a good picture of this. We understand mostly where the elements come from, which are the main processes that are producing these elements, and how these processes are evolving through time. But this is an ever-evolving picture, so every year or so, it changes a little bit. There is currently a lot of debate from the main site of production of the R-process elements, for example, if it's neutron star mergers or supermassive supernovae. But yeah, this is something that's currently evolving, and I'm going to show our work with the metal-poor stars can be directly related to understanding the sites of formation of some of the elements. And as I mentioned, the last parameter that is important for galactic archaeology are the stellar ages. But because the stars are evolving through time, their properties are changing, and we can use these changing properties of the stars to determine their ages. There are a lot of properties that change. For example, the atmospheric parameters of the stars are changing. This is something that we can model very well. We can, for example, plot isochrones in an 8R diagram to try to find the age of the star. The problem is, in some cases, the star is evolving very slowly, so it's hard to pinpoint an age. And in some cases, the isochrones are basically, I can show it here, the isochrones overlap in some regions, and they get too close to each other in other regions, so it's not always straightforward to determine ages this way. There are other parameters that change with the age of the star, for example, the rotational period, the atmospheric activity. This is just to mention that there are a lot of techniques, and there isn't a single technique that can be applied in all cases. And I believe this is the most, the main bottleneck for the studies of galactic archaeology right now is obtaining good, reliable stellar ages. Astroseismology is the method that's obtaining the most precise ages, but it also requires a lot of observational efforts. And the final topic that is important in this introduction is the topic of metal-poor stars. In this case, I'm not just talking metal-poor like metallicity below -1. We're actually interested in the ultra-metal-poor, hyper-metal-poor, and below stars, the stars that have metallicities below -4, which I'm going to show they can tell us about the population of the first stars in the universe. We don't observe right now the population 3 stars because We believe that in the metal-free environment, right after the Big Bang, the stars were formed were all very massive. So they only lived a few million years and enriched the interstellar medium. We don't see these stars nowadays, but we can see the stars that were formed from this first enrichment of the interstellar medium, and these are the stars that we are targeting. Because if we can find these stars and we can study do detailed studies of their abundances, we can infer the properties of those first stars in the universe. This is our main motivation. And the problem is that these stars, they are extremely rare. If you take one star like this at random, it's one every 100,000 stars is going to be an ultra-metal poor or below. And in 2019, when we started working with this, only 42 ultra-metal poor stars were known in the literature. So they are extremely rare. In S-PLUS, we already found 2 stars, but our studies were limited to the DR3 of S-PLUS. So we already can repeat our analysis that we've done already to search for more ultra-metal poor stars. But I'm going to show this result in detail. Before this, I'm going to talk about S-PLUS. Claudia is the PI of S-PLUS and was my supervisor, as you mentioned, for the 5 years I stayed here at IAG. And just to explain, I'll try to be fast, but also complete about S-PLUS. It is a survey that we're doing using the T80 South telescope. It's located in the Cerro Tololo Observatory. It's right besides Gemini telescope. We have the biggest dome, at least in this part here, but it's not the biggest telescope. I think there are bigger telescopes there, but we have the biggest dome. And it's a 80-centimeter telescope that is completely dedicated to S-PLUS, except for the 10% of the Chilean time. And this telescope has been observing the targets of S-PLUS since, I think, 2016. So next year is going to be 10 years of S-PLUS observations, at least. And this is a very important question that I think we need to ask, and we need to have a good answer for this, because the telescopes, they are getting bigger and bigger in size with time. So we're now, we, like astronomers in general, are building the new generation of telescopes. They're going to be 30 meters or more in diameter. And so this is the state of the state-of-the-art telescopes that we have so far. And we have the T80 South here at 80 centimeters. So we need to answer this. Should we be investing time, efforts, and our time and efforts in a telescope of this size? This is an important question. I hope I can convince you that yes. So I'm going to talk about the main characteristics of S-PLUS. The main one is the presence of the narrow bands. So we use the system of 12 filters. The broad bands are similar to the SDSS U, G, R, I, and Z bands. And the narrow bands, they are specifically chosen to be around some key spectral features. So they allow us to have sensitivity to some very important parameters. I'm not going to explain everything that we can do in S-PLUS, but I'm going to show that some of these filters here, especially the 395 filter, it's very sensitive to the metallicity, and it's what we can use to select those metal poor stars. Another very important aspect of the T80 South is the size of the field that we're imaging. So every time we point the telescope, we're observing 2 square degrees. So it's ideal for these large area surveys. And this is the, oh, I put the image on top of the footprint. But yeah, there is a, trust me, there are also fields here. So this is the footprint of S-PLUS. It's about 9,000 square degrees. This is the planet footprint. We are about 80% of the observations. Yeah, about 80% of this has been observed. I don't know if we're going to finish observing or the Monday finishes first, but we're going to get as close as possible to the original planet footprint. And this image here is just to show how the observations are done. The telescope is fully robotic, so during the afternoons, it plans the observations for the night based on the main priorities of what it should observe. And yeah, it plans the observations. Sometimes it requires some modifications, but usually the telescope works robotically, and it's what allows us to do this large survey. Here, just to show one aspect of S-PLUS, I'm totally focusing on my field of expertise here. There are a lot of things that we can do with S-PLUS, but one of the things that it is very good for is to estimate stellar parameters. So we have a few papers here that I am highlighting. The first one from Devin Withen, 2021, used neural networks, and he showed that we can obtain metallicities. Effective temperature is the easiest one to get, but he also showed that we can get good metallicities and good carbon abundances just from the narrowband photometry of S-PLUS. And in this case, you don't need to do spectroscopy to get at least the abundances for iron and carbon. And other works, also using machine learning, show that we can get, for example, the luminosity class, in this case also the log G of the stars. And in this most recent work, we expanded it even more to try to obtain as much abundances as possible with the S-PLUS filters. These are the elements that in the end we could get abundances for. So in some cases, the error bars are like extremely large, like 0.5 dex or more. But for some use cases, you just need a proxy or an idea of the abundances. So we included everything that could be measured. So S-PLUS uses 12 filters, has wide imaging. And when we look at the other surveys that are being done in the Southern Hemisphere, there are surveys that cover a larger area, like the x-axis here. There are surveys that go deeper than S-PLUS, so it observes fainter sources. But S-PLUS is the only one that includes, at least for these surveys at the time, it's the only one that includes the narrowband photometry. So those works that I mentioned that require the narrowband photometry, we need S-PLUS to do it, and it will remain this in the next few years. This is just to show a history of data releases of S-PLUS. So we are observing all that area, but we're not waiting to finish all the observations before releasing the data. We try to have data release each year. For now, we are constant in that. Every year we have a data release. And our most recent data release was IDR5 last year. And it covers almost half of more than half of the original planned footprint. It's going to become public this year, and we're also already working on IDR6, which is going to be released this year, we expect, for the collaboration. The results that I'm going to show are from a little bit older papers. So we focused on S-PLUS DR3. So everything that I'm going to show, the selection of the metal poor stars, was limited to the area that was covered by S-PLUS until 2022. So we can already search for more metal poor stars using the more recent data that we have in the past data releases. But as I'm going to show, we already have, from this sample using DR3, we already have more stars than we were able to observe with high-resolution spectroscopy. So we have, our problem now is time to observe everything that we want to observe. Another important thing that I need to mention is the tools for accessing data of S-PLUS. Now it's very easy to access S-PLUS data. There is the S-PLUS Cloud website with a very complete documentation on how to download the catalogs, on how to work with downloading images stamps, producing colored images as well. We are constantly updating this, but we now have already a very good set of tools to access the data. And just a quick advertisement in the middle of the presentation. I think it's the best time to talk about this. There's going to be the 20th S-PLUS meeting. We're having one meeting each year. And if you have any interest in S-PLUS, I think you must go to the meeting. We always have about 100 astronomers participating. I think it's important to mention S-PLUS is an international project. It's led by Brazilians, done in Brazil. Most of the funding comes from Brazil, but we have a lot of international collaborators. So it's a meeting that is definitely worth attending. It's open for submission of the abstract until July 25. Registration is until August 3. and the meeting will be held at Observatório Nacional between August 18 and 20. I really think it's a good idea to go to the S-PLUS meeting. So moving to the next topic now, I'm going to talk about the low metallicity stars. This was the main science project that I worked during my BEP with Vinicius Placo, who was my supervisor. And this study with metal poor stars already resulted in a lot of papers. So I think it's a very successful collaboration so far. And what I'm going to show now is basically the results of these papers that we published on this topic. I already showed this, the definition of the metal poor stars. This is basically repeating the first slide that I mentioned this. But I'm going to highlight the importance of these stars again. We are looking for these stars to observe the first population of stars in the universe. We cannot directly observe these stars. They are not in the universe anymore. But from the properties of these ultra-metal poor stars, we can directly measure the properties of these population 3 stars. I'm going to show we can measure the mass of population 3 stars, even though we cannot see them anymore in the universe. So how does it work? I mentioned the 395 filter. It is very sensitive to metallicity. This is synthetic spectra showing how the response of this filter changes depending on the metallicity. But it's not straightforward to measure an abundancy from a narrowband photometry. You have a lot of other parameters that are affecting the magnitudes as well. So what we do here in particular, because we're looking for a rare kind of star, so training machine learning models is very hard for rare objects. So what we did here is a very non-sophisticated approach, but works really well. What we did was find a color diagram that, using data from SDSS, we can see it's the one that creates the steepest gradient in metallicity. This was trial and error. We tried a lot of color diagrams with filters that we know are sensitive to metallicity, and then we found this combination that shows that the metal-rich stars occupy this region of the galaxy, of the diagram, and as you go down here, the metallicity, the stars become more metal poor. But this was for SDSS data, and there aren't many stars below -2.5, below -3, which are the stars that we are interested in. So what we did, we found this diagram using data for SDSS, and then we went to S-PLUS. This is almost the whole DR3 of S-PLUS. There are a few restrictions here, selecting only the stars, only the bright sources, only the sources that have detections in the 12 filters. But this is basically the whole DR3 that filled these conditions. And this is the region that we were looking in the SDSS diagram. And it was a guess initially that if the metallicity is decreasing in this direction, if we choose stars below this, we expect to find the most metal poor stars. So this was the first project. We had this guess that the ultra metal poor stars would occupy this region of the diagram, and then we selected all the stars that we could observe with this spectroscopy in this region here. So we did medium resolution spectroscopy using Blanco and Gemini South for this 522 stars. Took 1 or 2 years, and then we applied the stars were selected using the Scholar criteria that I showed before, and I'm going to show directly the result because of the time. And this is the metallicity distribution of the stars in this 522 stars selected using only color diagrams, and this is compared to other studies of studies targeting the selection of metal poor stars as well. And we can see that in comparison to these studies, we were able to select more metal poor stars, and including the 2 ultra metal poor stars that we are trying to find. So this is at the time, this was the main conclusion. We were able to find 2 ultra metal poor stars, but we still have a lot of contamination of non-metal poor stars, and we think we can do better than this, because this is us wasting time observing this star. We don't want to observe any non-metal poor star. We want to have a color selection in S+ that when we go to the spectroscopy, we are sure that we are actually observing the metal poor stars and hopefully finding more ultra metal poor stars. So what we did in a subsequent study was to characterize the sample as best as we could to understand where these non-metal poor contaminants were coming from and propose new selection criteria now that we have a sample that we know the metallicities, and then get rid of these non-metal poor contaminants. So we did a lot of characterization for the stars in the sample. For example, we obtained isochronal ages using the method of Jorgensen and Lindegren 2025. As I mentioned, obtaining ages for stars is not trivial at all. Like there are some cases where this is just to show a few age distribution, probability distribution functions. In some cases, yeah, we can get a good estimate for the ages. In some cases, we have something like this for the probability function, and yeah, the star exists. It's old, but we cannot say anything about the age of the star. So this is just to highlight that this is one of the most difficult parts to get reliable stellar ages. But the way we did was characterize the ages using the median of the distribution. Not exactly, there isn't an ideal way to do it, but when we characterize the ages by the median of the distribution, we see that we do have some young stars and some very old stars in the sample, but most of them have ages between 8 and 10 gigayears. The other characterization we did was the 6D phase space properties of the star. We got data from Gaia DR2 at the time. DR3 wasn't published yet. And we just selected the stars as, this is a Tonry diagram of the spatial velocities of the stars. And basically, this is the thin disk, this is the thick disk, and this is the halo, more or less. But this is a way to classify the stars. We did a classification based on the velocities, low velocities, medium velocities, and high velocity stars. And when we did the orbital integration, knowing these parameters, we can see a very clear picture of where these non-metal poor contaminants are coming from. So this is basically a side view of the galaxy. So what we are seeing here is the disk of the galaxy, and this is a top view of the galaxy. And I'm plotting here the orbits of all the 522 stars integrated over 10 gigayears. And we can see the non-metal poor contaminants are basically the disk stars. The disk stars that are young or intermediary ages, and they have low total spatial velocities. And the stars that we're interested in are mostly the stars in the halo. So it's not hard to get rid of these stars before going for the spectroscopy. So I'm showing here we had a lot of different criteria that we proposed at the time. The main result was that we could get to a selection. The more you select, the more you get rid of metal poor stars as well. So we had to find a balance. If our goal was to just get rid of the contaminants while still maintaining the ultra metal poor stars, we had a very good result that had only 0.6% of the remaining stars in the sample being contaminants. But in the end, we found a solution that didn't even use all this data. I think it's the best one because it doesn't introduce any kinematic and abundancy biases in the sample. It does introduce abundance, not kinematic biases in the sample. It's using another color cut. After we did the previous one, we include another color of S+, and we can see I don't have the labels here, but the yellow triangles are the non-metal poor stars, and most of them are above this line here. So just by introducing another color cut, we were able to obtain a very good, a much better selection for these metal poor stars. We basically get rid of the contamination of the non-metal poor stars with just another color selection. Okay, so what do we do with this now? We have this method to select. We have the medium resolution spectroscopy to confirm the nature of the ultra metal poor stars. And now we're going to target individual stars to see what we can infer about the properties of the galaxies at the very beginning of its formation. So the first one was a high-resolution spectroscopic follow-up of this star here. We don't have a better name for it. It's one of the ultra-metal poor stars that we have observed, and the high-resolution spectroscopy was done using the MIC spectrograph at the Magellan telescope. At the time of the publication, it was a letter because it was a very important new result, because at the time it was the ultra-metal poor star with the lowest ever detected, measured carbon abundance among all the other few. These were all the ultra-metal poor stars that were known at the time, and this one had a very low carbon abundance. So it was published as a letter, but 1 week after we published this, there was another paper that measured another ultra-metal poor star with a slightly lower carbon abundance. But this is the main result, the interesting part. So we have the abundances that we get from the high-resolution spectroscopy, the abundance pattern for this star, and since it's ultra-metal poor, I'm showing here that we can directly compare this abundance pattern to yields predictions of supernova. So a single supernova event is what is represented here in these abundance patterns here, and these events are for stars, for example, stars of different masses and resulting in supernova of different energies. And we can try to fit here which supernova model best fits the abundance pattern that we observe for this star. And in this case here, we can see that a star around 30 solar masses is the one that best fit this model. So we can say that this star was formed from the from the chemical enrichment of a single supernova, a single metal-free supernova in the beginning of the universe that had a mass of 30 solar masses. So it's a way to get properties of stars that we cannot observe anymore in the universe. So this was the first study that we did. We did another study 2 years later, another star that we selected from the sample. In this case, it's an extremely metal-poor star. And this one was observed with GHOST during the Science Commission of the spectrograph. And in this case, it was very interesting because we could get the light elements abundances as we did before and also compare it to yields of supernova. But we also were able to measure the heavy elements. And in this case, here's a comparison with models of neutron star mergers, which is a very important result because it's a debate if the neutron stars merger are contributing to the R process production. And in this case, we show that the abundance pattern is consistent with predictions from neutron star mergers. And we can tell the mass of the stars that, of this model, of course, but the model of these two neutron stars with 1.66 and 1.27 solar masses is what produces these chemical patterns that we are seeing here. The last example of this, this was last year. This one doesn't come from this sample I'm showing because it's part of this study as well. It's a much brighter ultra-metal poor star. I say ultra-metal poor because I didn't include here the error bar, but if you consider the error bar with about 0.1 dex, it could be an ultra-metal poor star. And this one is very bright, so we observed it using the 3.5-meter telescope at the Kitt Peak Observatory. This is very hard. But the most interesting thing about this star, the idea was to do the same study I'm going to show here. We fitted the yields of supernova, different stellar mass than what we get for the other one. But this is the part that I think is the most interesting for this star. This was my main contribution for the paper, so I'm very biased. But this is what I think is the most interesting part for this star. This is an ultra-metal poor star, but it has the orbit of a disk. I triple-checked this before even talking to any of the collaborators because we don't expect the ultra-metal poor stars to have these disk-like orbits, because we believe the disk was formed about 10 gigayears ago, 8 to 10 gigayears ago, And at the time the thin disk of the galaxy formed, we believe the interstellar medium was much more rich than what would form a star with metallicity below -3, for example. So we went to try to understand more about this star. We tried to get the isochronal ages as well, but very hard to get a precise age. The mass of the star we could constrain. It's consistent with a mass of a star that's going to live this long, but we couldn't say much about the age of the star. We applied another method that I won't have time to explain here in details, but it's based on the kinematics of the star. It's a method that assumes that the stars are born in circular orbits and they evolve. The orbit evolve through the interaction, the gravitational interaction of these stars with the other components of the galaxy as the star orbits the galaxy. And there is this method that I published in 2018 that uses the velocities to obtain a probability distribution function for the age of the star. So we applied this for this star, and the kinematical age would place this star at 13 gigayears. But this assumes that the star was born in a circular orbit, so it's a bit of a stretch. But in the lack of better alternatives, we included the result as well. But what this is showing us is that there is a star, ultra-metal poor, in the orbit of a disk. So we looked in the literature. We were able to find other stars already known with these properties. So it's a group of 4 stars that are known, extremely metal poor stars, or ultra-metal poor stars, that have these orbits with very low Z max. So there's this star that we know, and other stars in the literature as well. So we know now that there are stars in the thin disk or thick disk. It's debatable, but there is stars in the disk of the galaxy that were formed that had the metallicity of the earliest stage of the universe. So it completely challenges the idea that the thin disk formed 10 gigayears ago. It must have started to form much earlier than this. This is obviously a very strong affirmation to do for just one star, so we need to keep studying this. But there is other papers published last year. This one is a completely different approach, but also trying to obtain ages for stars in the thin disk, a paper by Samir Nepal, and showed that there are stars in the thin disk that are older than 10 gigayears. So there are some works now that also agree with this affirmation, and this is something that I think we need to explore much further in future studies. I don't know how I am with time. I'll try to show a few more of the ongoing research now. So this is just to tell that we're still doing this kind of work. So we're still doing high-resolution spectroscopy. We already selected more stars. 2 of them have been observed with the GHOST spectrograph last semester. I still need to analyze the data. I will talk more about this in the last slide. But we already have stars observed, and we already sent new proposals to continue studying these stars that we're finding in S-PLUS. And now we're interested in other questions as well, like does the stars that belong to accretion events in the galaxy, the remnants of accretion events, does the chemical abundance pattern of the ultra-metal poor stars in this structure follow the same ones that we're seeing in the Milky Way? And this is one of the things that we plan to be able to answer with this. One of the stars we selected is a remnant from the Gaia-Enceladus merger of the Milky Way. So just to quickly mention a few studies that we have. This is a result that we have for a while now, but still didn't publish, but the result is ready. We need to finish this. We measured the metallicity gradient in the Sagittarius stream. So now this is also galactic archaeology study, but instead of individual stars, we're looking at a larger data set, and we were able to measure the metallicity gradient. We compared with spectroscopic results, and we showed that it's very hard to get the gradient because the uncertainties for the photometer is very high, but we are reproducing what can be observed with spectroscopy, but we have much more stars in our data set. And the main result that we have, we were able to compare the measured gradient with predictions from any-body simulations, and this allowed us to constrain what was the original gradient in the dwarf spheroidal galaxy that originated the current Sagittarius stream. And when we compare the gradient that we measured with other dwarf galaxies, we can see that the value is consistent with what we expected for the dwarf galaxy that we observe in the local universe. So it's a very, very strong tool that we can also use S-PLUS to get the data for something like this. Another very quick result that I'm going to show is from Guilherme Volutavicius, doing a PhD here. And this is just to show what happened in the past in the halo of the galaxy. The halo, we believe there is an in situ formation, but not most, it's debatable. A lot of stars in the halo was formed in these accretion events of different proto-galaxies, different dwarf galaxies that were accreted by the Milky Way, that merged with the Milky Way during the formation. This was theoretical work until a few years ago. Sorry. Yeah, the video wants to stay on top. Yeah, okay. So this was theoretical work. This is not from the same video that I showed. It's another paper showing the same thing, but the figure is better. Those different color groups, each individual proto-galaxy has specific dynamical properties that depend on the velocity, the angle, the approach, the way it approached the Milky Way. And these properties, what this plot is showing, is that the original properties of the proto-galaxy in some parameter space, like the energy versus angular momentum, it's conserved through time. Even after 12 giga-years, you can still see the groups. So until a few years ago, this was only from simulations, but from Gaia data, we can now see these structures in the real data that we are getting, especially with Gaia DR3. And what we're doing in S-PLUS is selecting this, it's what Guilherme is doing in S-PLUS, selecting these, the stars based on the kinematic parameters from Gaia, and using the metallicities, the photometric metallicities from S-PLUS, characterizing these different substructures. So it's also another powerful use for S-PLUS. And in particular, he showed that there is a very important diagnostic plot that depends on the abundances of manganese, magnesium, and aluminum that tells us if the star is accreted or formed in the Milky Way. And we showed that with color combinations in S-PLUS, we can also select these stars. So everything that is red here is what is within this part of the diagram that selects the accreted stars. So we can use color diagram in S-PLUS to also tell if a star was formed in the halo of the galaxy or if it was accreted at some time. I'm almost done. So what's next? I'm currently, as Claudia mentioned, I'm at INPE with an Auxílio Jovem Pesquisador, FAPESP. So I have a lot of different projects that FAPESP gave me the funding to work. Now I have to actually work on them. So I'd like to advertise a few projects. Two of the fellowships are already filled at INPE, the master fellowships, but I have a PhD fellowship to work with this high-resolution spectroscopic follow-up of ultra-metal poor stars, but also undergrad IC projects to work with calibration, with characterization of stellar streams in S-PLUS, and also I mentioned the kinematical method to determine ages. There is a project, this one's not related with S-PLUS, but the use of kinematical ages to find the ages of stars with astrobiological interest, which is stars with known exoplanets in the habitable zone. So my email is here, so if anyone is interested, if you know anyone interested, please let me know. And the take-home message is just to finish. Ultrametal poor stars. They are fossil records of the earliest stages of the formation of the Milky Way, and S-PLUS is a very powerful tool to select these stars. We have already discovered 2 just in DR3 of S-PLUS. And also, I showed for these ultrametal poor stars, we can find chemical abundance patterns from single nucleosynthesis events, like a single supernova or a single neutron star merger. And that's it.
Thank you very much, Felipe. Any questions? Please go ahead.
Thank you for interesting talk. I'm interested in this BD plus 44 stars orbits.
Okay.
So could you go on that slide?
This one.
Yeah. So here you can see the angular distance traveled by two successive periastron or apastron point is greater than 2 pi.
You mean the
yeah,
here.
you can see the next orbit will shift in the opposite direction as the the particle or stars orbiting directions. So is there any particular reason? Because the generally the star will have a prograde precision or shift. Here it seems like a retrograde precision.
No, it's not. It's a prograde.
No, then the angular distance traveled by two apastron, or you can consider periastron point, is greater than 2 pi.
Okay. I should check that. But from the LZ value, maybe I plotted it inverse.
I'm also looking at your this paper because it seems like a retrograde or negative precision, because the next orbit will shift in the opposite direction as the particle is orbiting.
Okay.
So is there any some matter distribution and everything? Because the apastron point is like a 16 or something like a 8.6 kiloparsec, and the galactic center from our distance is 8.2 kiloparsec.
No, sorry, what?
So we are residing from the galactic center. This orbit is residing in the Milky Way, right?
Yes.
Yeah. So we are residing around 8.2 kiloparsec from the center.
Yes.
And the apastron or maximum point you can consider in your paper is cited like 8.6 kiloparsec.
Sorry, I didn't understand.
Oh, we'll discuss further.
Yeah, we can discuss.
Yeah.
Sorry.
Thank you.
Okay.
Thank you very much. Who else? Ah, yeah, Gaston.
Hi, very nice talk. Thank you. And I was about to ask about this same star also.
Oh, okay.
And my question, I think, is simpler. It's well, you can see that's a very elongated orbit.
Yes.
That's precessing. But could this star be? And I understood that you think this star is born in situ, is born in the Milky Way.
That's we don't have enough to claim if it's accreted or if it's born in the Milky Way.
Be my
but
question.
it's a good question. You mean it has a high eccentricity?
Yeah.
Yeah. This is related to this evolution of the orbit. So if this star was born in a circular orbit, the disk heating, the kinematical heating of the disk, would take this amount of time to heat the orbit until this vertical displacement and this eccentricity. Okay. So if the star is old, as we expect for the metallicity, and it would have enough time just by orbital evolution in the disk of the galaxy to reach an orbit that is as that has an eccentricity as high as this one and high Zmax as this one. So it can be old enough to have this, but it could also be accreted. Okay. So we can't rule out any of the. That's why we need to study many more stars with these properties to be able to say something, to generalize about this.
Okay. And I have another question. It's a more naive question. You said that there's one of those stars, very poor, with very low metallicity, would be born from a single explosion of a population 3 stars. Is that right?
Yeah. What we're saying is that we can fit the model of a single supernova to the abundance pattern that we observe for this star. It could also be a combination of different. But what we are saying is that one is enough.
One is enough.
Yeah.
Okay. But is it realistic?
Yeah. I mean, yeah. One is that's why this stars is so rare. One event is enough to enrich the interstellar medium up to this value. This is extremely realistic. We're showing, for example, yeah, we would need. Where's the first one here? We would need a 30 solar mass star to get to this abundance pattern, but we expect the first generation of stars to be to have an IMF much more massive stars than what we observe today. So it's realistic.
Okay, thank you.
Yeah.
I have a question, Felipe. You did this with DR3, which was just 2,000 square degrees on the sky, and we are going to soon have 6,000 square degrees, so 3 times more. And the other thing is that we have now much better determinations of the metallicities. Have you looked at these 2 stars that you found at -4? What are the metallicities that the people who have done the latest papers on the metallicity determination, what is the metallicity of these objects determined from the 12 filters, so that can better guide us to the very, very low metallicity stars?
We did check this a few days ago, actually, when the Basish was here at IAG. We checked that. I think only one of the metal poor was in his sample, and it was -2.5.
I see.
So, but -2.5 was the lowest value he got. So it's basically what I was mentioning.
Yeah.
With the machine learning, we cannot go to these very low metallicities because we don't have the training set.
I understand that the group of Marcelo Borges, who is now working with S-PLUS and with the simulated data, he is able to get to lower metallicities.
No, I think Marcos Vinicius still goes just to -2.5.
-2.5, okay, yeah. Thank you.
I think Devin in the 2021 paper included simulated.
I see.
But I think it was to go to -3, not -4.
Okay, thank you. Anybody else has any questions, Laerte?
Regarding the semi-plot, we can see that some of the points are well fitted by the supernova, but not the others. What is the reason?
Yeah, the reason is the error bars are very large. So basically the best fit. But this was the worst one. The other ones, I think the fitting is much better. But yeah, the error bars are large, basically.
Okay, thank you.
Anybody has questions online? Let me see. No? Is anybody else here? Questions for Felipe? Felipe, thanks again for a wonderful talk. Very informative. Thank you. Okay, there is coffee and tea outside for people to confraternizar.